Union find, also called disjoint set union, is the data structure you reach for when groups are changing over time and you need to keep asking whether two items belong to the same connected component. In this tutorial, I want to start from the problem it solves, compare the older ideas, and then build the optimized version with path compression and union by rank. Think of a stream of operations. Some operations connect two nodes. Other operations ask if two nodes are already in the same component. Recomputing the full graph after every change would be too expensive, so union find gives us a compact structure that keeps only the connectivity information we really need. This is the most important picture to hold in your head. At time 0, every node stands alone. The parent array says each node points to itself, so each one is a root. Later, a set is represented by whichever root its members eventually climb to. Historically, one early idea is called quick find. It makes membership checks simple because every node directly stores a component label. But the moment two components merge, you may have to walk the whole structure and rename many entries. So quick find is conceptually simple, but unions are too costly for serious use. Quick union is much closer to the modern idea. Instead of storing component labels directly, we store parent pointers. That makes union elegant because we can merge by connecting one root under another. The problem is that if we do this carelessly, the trees become tall, and then every find call has to climb a long path. So let me frame the progression clearly. Quick find gives you simple queries but terrible unions. Quick union gives you a better structure but can still degrade into long chains. The optimized version combines parent pointers, path compression, and union by rank so both find and union stay efficient over long sequences of operations. Here, node 6 has to walk 6 to 5 to 4 to 3 to 2 to 1 to 0 just to learn its root. One query is already expensive, and repeated queries stay expensive if we never improve the structure. So now we need the two classic optimizations. Path compression says, if I already walk that whole path, I should not pay for it again later. So while the recursive or iterative find returns, every node on that path gets required to point directly to the root. After one expensive lookup, the next one becomes almost trivial. Path compression repairs trees after we use them. Union by rank tries to prevent bad trees from forming in the first place. If one root already represents a deeper tree, we keep it on top and attach the shallower root under it. If both ranks tie, we choose one root and increment its rank by 1. After union 0, 1 and union 1, 2, the first component has root 0. After union 3, 4, the second component has root 3. The data structure does not care about the order inside a set. It only cares which root represents that set. When we union 2 and 4, we do not directly attach 2 to 4. We first find their roots, which are 0 and 3. Because the ranks tie, we can choose one winner, attach root 3 under root 0, and increase root 0's rank. That is the balancing rule in action. This is the beautiful part of union find. Even a connectivity query helps future operations, because find does useful maintenance work. Node 4 used to point to 3, which pointed to 0. After one find call, node 4 now points directly to 0. There are 3 classic union find bugs. First, people attach one input node directly under another instead of merging by root. Second, they forget that path compression belongs inside find itself. Third, they update rank too often, even when one root was already strictly deeper. If these 3 rules are clean, the implementation is usually clean too. Writing code, it helps to say the contract out loud. Find returns the representative root. Union merges by root and returns whether a merge actually happened. Connected is just a convenience wrapper that checks whether 2 finds end at the same root. Here is the find method. If X is not its own parent, we recursively ask for the root of its parent, then overwrite parent X with that root. That one assignment is the entire path compression idea. The union method begins by finding both roots. If the roots are already equal, the nodes are already connected. Otherwise, we keep the larger rank root on top, attach the other root underneath it, and only increment rank when both trees had the same rank before the merge. Here is the whole class in one place. In practice, this is the version you will reuse in Kruskal's algorithm. Connected components questions, account merging, graph redundancy problems, and many island-style optimizations. The final result is why union find is so popular. Once both optimizations are present, operations become almost constant in practice. The formal analysis uses the inverse Ackermann function, which grows so slowly that for programming interviews and real software, it is basically flat. For more LeetCode practice, follow and subscribe to the channel. This is AI and human collaboration.